Hi, good morning to all those who are viewing this video. Myself, Mr. A. Balachandran, Assistant Professor in the Department of Electronics and Communication Engineering from K.S. Rangasamy College of Technology, Tiruchenur. In this session, we are going to see the power dissipations, that is power dissipation in the Cmos circuit. There are the two components of power dissipation is available in the Cmos circuit. That is, one is a dynamic power dissipation and another one is a static power dissipation. It is nothing but in the dynamic power dissipation, we categorize the two things. That is, one is the power dissipated during the signal transitions. That is, for example, in the inverter, if the input transition is occurred from 0 to 1 or 1 to 0, or any signal transition occurs, means it is coming under the category of dynamic power dissipation. And the next one is short circuit power dissipation. In the short circuit power dissipation, we can say that for the fraction of seconds while the signals are transferred from the one position to another position, there may exist a short circuit from the power supply to the ground. It may cause some power dissipation in the circuit. That is coming under the category of short circuit power dissipation. These two are coming under the dynamic, that is the signal transition, and short circuit power dissipation is coming under the dynamic power dissipation. And next one is static power dissipation. It is nothing but a leakage. The overall we can say that the total power dissipation is equal to the summation of the dynamic power dissipation and static power dissipation. The dynamic power dissipation further categorized into two types, that is a transition, that is signal transition power dissipation and short circuit power dissipation. These are shown in these equations. Next one is we are going to see that deeply that Cmos dynamic power dissipation. Here you can say that this is an example for the signal transitions. You can see that Vi is an input, V0 is an output. From this V1, Vi, that is the signal is transferred from 1 to 0 and 0 to 1. During that time, the capacitor is charging and discharging. And also the output is changes from the 0 to 1 and 1 to 0 for the Cmos inverter circuit. You can say that is for the fraction of second from 0 to 1 and 1 to 0, while the input is transferred from one position to another position. You can see that ISC, that is this ISC is created due to that these two transistors are in on condition at the same time. That is, PMOS and NMOS transistors are both the transistors are in the on condition for the fraction of seconds, or it may be the time taken for the signal to transfer from one position to another position. This will create the short circuit, and due to the charging and discharging of the capacitor also the power can be dissipated. For that is we can conclude by the formula, that is VCL into VDD square by 2. That is, CL is nothing but a load capacitor and VDD is nothing but a power supply. Yeah, this is the dynamic power for the signal transition dissipation. That is equal to summation of 0.5 alpha I f clock CLI VDD square for all gates. That is, approximately we can say that alpha 01 f clock CL into VDD square. These are all in the multiplication, where alpha is the average gate activity factor. Alpha 01 is equal to 0.5 alpha, average 0 to 1 transitions. F clock is the clock frequency, CL is the total load capacity, VDD is supply voltage. And then the next one is in short circuit power. As I told you earlier, the short circuit power is consumed by each transition. That is, it will increases with the input transition time. It requires to reduce the short circuit power, it requires the gate output transition should not be faster than the input transition. After the input transition occurs, then only the output should changes its position. In that way, we have to design the circuits. And also increasing the output load capacitance reduces the short circuit power. And scaling down of supply voltage with respect to threshold voltage reduces the short circuit power. And next one is how we are going to reduce the dynamic power. For example, if, we know that dynamic power dissipation is occurred due to the signal transition and the short circuit power dissipation. To reduce the signal transition, we will see the reduced voltage operation with voltage scaling and capacitance minimization and with the device sizing. To reduce the number of transitions, we have to eliminate the glitch elimination. Glitch elimination, it is nothing but we have to reduce the hazards in the circuits. We know that we have the different hazards, static hazard, dynamic hazard, and so we have to reduce the hazards in the circuit so that we can reduce the glitch, and also we can reduce the power dissipation in the circuit. And next one is an Cmos static power. That is, static power is nothing but an leakage power reduction. So leakage, we know that in the Cmos we have the two transistors, that is PMOS and NMOS transistors. Both are fabricated in the P well and the N well, because we have the both the transistor. For example, to design a NMOS transistor, we need the P substrate. To design a PMOS transistor, we need the N substrate. So when we have the P type and the N type, then automatically there exists an PN diode structure. In the PN diode structure, exist means there is a possibility of having the forward bias and reverse bias. We know that the basic PN diode operation, in the reverse bias, there is always a leakage current is possible. So during the operation, then due to this, the P structure and the N structure, there will be existing an leakage currents in the reverse bias condition. These are the different components for a leakage current. First one is in subthreshold conduction. Next one, reverse bias PN junction diode conduction, that is called as an ID. Then gate induced drain leakage, IGIDL, due to tunneling at the gate drain overlap. Drain source punch through and gate tunneling, IG through thin oxide. How we are going to reduce the leakage power? It is a fraction of the total power increase as clock frequency drops. Tunneling supply of unused parts can save power. For a gate, it is a small fraction of the total power. It can be significant for very large circuits. Scaling down features requires lowering the threshold voltage, which increases leakage power, roughly doubles with each shrinking. Multiple threshold devices are used to reduce leakage power. Yeah, thank you. Thanks for watching.